So here we are with segment 2 for chapter 2, elements, compounds, and the periodic table. We had left off with molecules and chemical formulas. So at this point we had broken the periodic table down into the three groups of metals, metalloids, and nonmetals, and talked a little bit about the properties. Next we want to start to make compounds, so molecules and chemical formulas. So it's useful to visualize atoms, compounds, and molecules. So your atoms can be represented by a sphere. And then, of course, if we have different colors for different atoms, it kind of gives the idea of two different things coming together. So your standard scheme is over here on the right. So if you were to pick up a molecule set, and if you're a chem major, I would suggest that you can get a moly mold. You can find them probably at Amazon, relatively cheap, all the way up to really expensive, depending on what you want to spend. I think my personal set is about $25. Now that was, many years ago, but I honestly don't think the price has changed much. But if you get a general set, then it's going to give you mainly your carbons, your hydrogens, nitrogens, oxygens. After that, you may or may not have these different ones. Sometimes we get some chlorines in there. I've seen some with sulfurs. Typically, they'll give you one that's like a silver metal ball that has a bunch of different potential holes on it to make different molecules. All right. But that's, again, if you're a chem major, I would suggest picking one up. The earlier the better. If you're not a chem major, it's kind of up to you. The better you are at visualizing things, the least likely you are to need the model kits. As chem majors, even if you're good at visualizing things, eventually the molecules get large. And so if you have a set, it's just easier to manipulate things and see where things are. So for molecules are going to be atoms that are combined to form a more complex substance, right? Now for molecules, it's going to be discrete. So they have a definite edge, definite ends, right? And each one will be composed of two or more atoms, and it will repeat. So for instance, molecular oxygen is O2, carbon dioxide, CO2, ammonia, NH3, something like sucrose, and this is what I mean, chem majors, you can get more complex, C12H 22O11. So again, sugars start to get to be really big molecules, and then of course we have what's called a polysaccharide, poly meaning many, saccharide is sugars, and so you start putting it together and you make really long sugar chains. All right, now the formula just tells us the composition of the substance. So again, if I'm going kind of fast, it's because we typically believe that you guys know this stuff already and we're just knocking rust off. So chemical symbols, we represent the atoms by elements that are present. We use the subscripts that tells us how many of each atom is in the formula. So when we say Fe2O3, we know that there's a 2 to 3 ratio between iron and oxygen, right? Now, free elements, the element not combined with another in compounds. So we just use a symbol to represent those. So if it was just a free element, we would just say iron, Fe, right? So Fe plus something, something, something. Right? Sodium, same way, neon, aluminum. The diatomic molecules will now be with subscripts of 2. Okay, and there's 8 of those that always want to come in pairs. So your diatomics will be hydrogen, which is number 1, and then it's called the plus 7. So 1 plus 7. The 7 is starting with nitrogen. Nitrogen is number 7 on your periodic table, and so it makes the top of the 7 by looking at nitrogen, oxygen, and then fluorine. And as I mentioned in the first segment, all of 7A is going to be diatomic. So that makes the leg of the 7. Now, you're going to need to be able to depict molecules. You'll need to be able to draw them eventually. It takes practice. Again, you'll need to be able to visualize these, and we'll be worried about shapes a little later on. So we're going to concern ourselves with the shape of molecules simply because that's the reality of it. It determines where things are going to react, how things are going to react, how the formulas are going to be made in some cases, electronically, how they're put together. And so there's just a lot of good information. If we can visualize the structural formula, we'll be better off. And of course, you can use the model kits. You can get a ball and stick model kit. You can actually, and I'll see if I can remember to do this, post a website called JMOL. It's a capital J and then MOL. Just in case I forget to post it, you can always go check it out. And it will allow you to put in formulas and go through these 3 types of visualizations on the computer, so you won't have to actually purchase a kit. But it'll give you the structural formula, it'll show you the ball and stick, and then it'll fill it in with space. So given the atomic distances, the atomic radii, it will look at the bond lengths and put all that together for you and then fill the space that these atoms would actually occupy when they come together to make those molecules. So structural formulas would look something like this. For water, we might write it out as HOH, H2O, right? Methane would be CH4 or C with the tetrahedral 4s around it. So this is going to turn out to be a tetrahedral. We draw it on a piece of paper at 90 degrees, but we're going to learn this semester, if you didn't already know, that that angle is actually a lot larger than 90 degrees. Okay. So let's see. For the space filling, we get 3D representations that look more like this, where we have the hydrogen molecule, and now you can see it's like the ball is just kind of big. It's called hence the space filling, so it shows how it goes together. And then here we have the ball and stick model. So the ball and stick model, you can see it's like taking little balls and little sticks, putting them all together. The sticks would represent the bonds, kind of linked together. There's a couple examples of that. And then the space filling molecules would look something like that. So when it's not diatomic, you can see we show the overlap in orbitals, and we'll talk about this in bonding theory, what's going on there and why it's not like two spheres pressed against each other, but actually melded together. Now, the more complicated the molecule gets, it gets a little more complex, a little harder to understand, but we can break it down by parentheses, all right? So how do we translate this structure? So here's urea, CO, and then we say NH2. Well, if I look at CO, here's the CO in the middle, and now I've got an NH2 over here and an NH2 over there. And again, you might be familiar with the parentheses, but anything in the parentheses gets multiplied by the subscript outside the parenthesis, right? So if I expand that out, 2 times 1 gives me 2, and then 2 times 2 gives me 4. Now, atoms in parentheses simply appear twice as a unit, is what that's telling us. Now, something new for us that we might not have seen before are going to be hydrates. So hydrates are crystals that contain the water molecules. So if I take a material and I dry it out, completely dehydrated, it's actually a powder, which it's interesting, but not, it's not like ooh, ah, and it's not pretty. It's usually just a white powder or a yellow powder, or I'm trying to think some of the other more popular colors, maybe an orange powder. But when we actually take our time and crystallize it, which is a technique, and we'll try to work that technique out when we look at aspirin right away, one of our first labs. When we do that, what happens is the water will actually fill in the space to make the crystal very patterned, and we call that a hydrate. So when we take calcium sulfate and it's got the 2H2O in it, then it's going to look a lot prettier and it's going to make a nice crystal, right? Now the water itself is not tightly held, and so here they're showing you the experiment where you can dehydrate it. So we're going to take that pretty blue crystal, we're going to heat it up, and as we push that water off of the molecules, boom, it starts to turn a white in there, and you can kind of see that, and that's dehydration, obviously. So we're going to remove that water via heating. And so on this side, we get a nice blue, pretty crystal, which is a pentahydrate. And on the other side, we get just the white powder, right? Because the hydrate is gone now. The remaining solid is called anhydrous. So when you're looking at labels in the lab this semester, we'll see this a couple of times. We can have calcium sulfate, or here I'm sorry, copper sulfate pentahydrate, and then you'll see copper hydrate, or excuse me, copper sulfate anhydrous. That's going to be your CuSO4, which means you're probably going to have a white powder. Now, through all of this, you got to be able to count those atoms. So whether it's a hydrate or whether it's a metalloid or non-metal, keeping track of your atoms. We know it's the subscripts that are going to matter, right? So the subscript tells us how many of each atom is in the formula, and the quantity in parentheses means it's going to be repeated twice. Kind of showed that already. And of course, if you have a raised dot, that means it's going to be a hydrate. So should have pointed that out. Let's flip back just real quick. So here, when we write the hydrate, it's calcium sulfate, and then you have a dot here, and then 2H2O. So it's telling us how many hydrates are there. The dot separates it out because it's actually two different things. All right. All right. So counting atoms then, for an example, here we have CH3,3COH. Subscript 3 means that we have 3 CH3 groups. So that means just from that alone, we're going to get 3 carbons and 9 hydrogens. That means total now, I have 3 carbons coming from the CH3 groups, but I also have 1 carbon outside of that formula, which means I have 4 carbons total. For the hydrogens, we know we have 9 hydrogens tied up in the CH3s, and then we have 1 hydrogen here in the formula, so that's going to give us 10 hydrogens. And then last but not least, we have 1 oxygen. So altogether then, we'd have 15 atoms, right? So we'd have 4 carbons. This mouse is not, there it goes. We have 4 carbons, 10 hydrogens gives me 14, plus 1 oxygen would be 15. Example number 2. So here we have 2 COCl2.6H2O. So the dot means we have 6 waters, which means we can multiply both H2 and O by 6. So that means there are going to be 12 hydrogens and 6 oxygens just for the water alone. Then we have 1 cobalt, and of course we have 2 chlorines. So when I sum that up, now I get 12, 6, 18, 19, 20, 21. All right, hopefully that makes sense. All right, in fact, you might even be bored, right? So if you are, I'm sorry, but let's get this done and we'll be, yay, much the better for it. And for those of us that are not bored and we're still working this through, then that's all right. Take your time and practice. Make sure you get this down because this is all stuff you're going to need later. All right, so your turn. Count the number of each type of atom in the chemical formula given below. So we have Na2CO3. I'll pause. You can pause the video here, write out your answer if you want. We're going to have 2 sodiums, 1 carbon, 3 oxygen. How about the NH42SO4? And again, I'll leave a pause. And then 2, 8, 1, and 4. For C, we have Mg3PO42. Whoops, went a little fast there. I didn't give you the pause. So you have 3 magnesiums, 2 phosphorus, and 8 oxygen. For D, we have our copper sulfate pentahydrate. Give you a pause again. We have 1 copper, 1 sulfur, 9 oxygen, and 10 hydrogen. If you didn't get the 9 oxygen, remember you got 4 for the sulfate and then 5 from the water. All right, let's see. C2H5 twice, N2H2. Give you a pause. And then 4, 12, and 2. So don't forget you got to multiply there it goes. You have to multiply this 2 through to give you 4 carbons here. 2 there gives you the 10 hydrogen there, but don't forget you have to add these 2 out here. All right. What are the formulas of the compounds shown? So here we've given you the different models. So here are your different models, and then here's your color code key, so you can figure out which is which. So are the molecules there? These 3 respectively. All right, so you have C3H8, CH3NH2, C3H6O2, and of course this would be the first one, the second one, and then the third one. And then I'll pause here for a sec, give you a chance to work this out for yourself. And hopefully you got an A. All right, that's going to bring us to Dalton's atomic theory. So we're going to start to put together how the history of all this works together. So we now have tools to explain the theory and its consequences. All molecules of compounds are alike and contain atoms in the same numerical ratio. For instance, water is H2O and it's always 1 to 2, right? So there's always going to be 2 hydrogens to 1 oxygen. Oxygen weighs 16 times as much as hydrogen. Hydrogen is 1 mass unit, where oxygen is 16. And then, of course, atoms in fixed ratio by mass, then if we have 2 hydrogens and 1 oxygen, we have 2 to 16. If I have 5 waters, now I have 10 to 5, which means 10 to 80. Right? So it's just multiplying out by 5. So you always have that repeating pattern. Now, successes for Dalton's atomic theory. He explains the law of conservation of mass. Right? Chemical reactions correspond to rearranging the atoms. So we don't create or destroy any new atoms. We also explained the law of definite proportion. We just saw that, right? Given a compound always has atoms of the same elements, it's always going to be the same ratio. It's predicted by the law of multiple proportions. This is not yet observed, but some elements combine to give 2 or more compounds, right? So for instance, SO2 and SO3. So Dalton's atomic theory, we haven't been able to prove that it will do that for us just yet. Now, when 2 elements form more than one compound, different masses of one element that combine with the same mass of other element are always in a ratio of small whole numbers. What? That seems crazy. When 2 elements form more than one compound, different masses of one element that combine with the same mass of other element are always in a ratio of small whole numbers. So atoms react as complete whole particles. Right? So for instance, what they're telling us is if I have sulfur dioxide and I have sulfur trioxide, we have oxygens and sulfurs, right? So in SO2 we have 1s, 2 O's. Sulfur trioxide we have 1s, 3 O's. The mass of sulfur is 32.06 in both of those. The mass of oxygen, we get 32 in one and then 48 in the other. Now we can use this data to prove the law of multiple proportions. So here's how we're going to do it. Sulfur dioxide, sample size 64.06 grams. We have 1 mass of sulfur, 32, 2 masses of oxygen for 32. For sulfur trioxide, we have a total mass of 80, 32 coming from the 1 unit of sulfur, 48 coming from 3 units of oxygen. The ratio of oxygen in SO3 to SO2 would be 3 to 2. All right, hopefully that made sense. All right, so molecules small and large. So far we've discussed only the small molecules, but some are very large, especially those found in nature. All right, same principles will apply, for instance, DNA short segments. So here we show you the DNA, and you can see the space-filling molecule, and this is just a short segment of it. Now, obviously, it keeps going further and further, but you can see the helix going around, right? How do we know the formulas? Right, it's hardly out of the blue. So when a compound is first isolated, we don't know what the formula necessarily might be, right? So how do we figure it out? Well, we're going to back that up with extensive experimentation. The results of the experiment to determine formula, chemical reactivity, of course, molecular shape. We can speculate this once the formula is known. So in my own research lab when I was a grad student, what we would do is we would create a compound and then we'd have to do several different analyses on it. The first thing we would do is called an NMR, so nuclear magnetic resonance. And so we would run what was called a carbon NMR. And so you're looking for just carbon atoms, right? And so this machine would tell you how each carbon atom is related to other carbon atoms in the same environment. Then we would do a phosphorus NMR and a nitrogen NMR. So those are just 3 of the elements that were in our compounds. So that would be the first set of tests. The next test we would do was called elemental analysis. And so we would actually ship that out. So we would send that to another lab. And what they would do is burn our sample in the presence of oxygen and then report back the carbon, nitrogen, and oxygen percentages. And that needed to match up with the formula we thought we had synthesized. So once we had gotten the NMRs and then we had the elemental analysis, if all of those were checking out and was looking good, the next thing we would do is called X-ray crystallography. So we would do X-ray diffraction, single crystal X-ray diffraction. And from that, what it would do is measure all the different nuclei, right? And based on where the nuclei were located, it would start to tell us the distances between different nuclei. And based upon how it would rotate around and basically ricochet the different radiation, that would tell us the angles of incident and the size of the nuclei. So we knew the size of the nuclei and we knew their relative position, which would give us a really good bearing on what was actually there based upon what's been seen in the past. And from those four pieces of information, we would determine that we either had that formula structure or we didn't. And if we did, typically it would lead to a publication, and then it would actually move on into part of the other part of our research projects. All right, so typically there's a lot going into it. You might have heard of gas chromatography. That's another popular one. We didn't use that in our lab because we worked with metals, so we had organometallics. And so those things are typically solids. And so obviously with chromatography, you need it to be either a liquid, HPLC is high pressure liquid chromatography, or GC is gas chromatography. So our materials wouldn't work for either one of those. But I was also spent time in an organic lab where we would do a lot of HPLC. So it's a very quick and I shouldn't say quick and easy test. It can be a pain to set up, to be quite honest. But once it's set up, it is quick and easy. It's a push a button, and then 20 minutes later, you have your results. Especially if it's on compounds you're already familiar with, so in a production sense. So that's the other thing you got to keep in mind. Usually, when we're talking about we don't know the formula yet, you're not in a production line, you're in a research line. And so you're going to have a lot more access to a lot more instrumentation in that situation. All right. Now, to visualize mixtures, if we look at mixtures at the atomic molecular level, you can think of it as just kind of mixing them together, right? So different color spheres stand for two different substances. So here in A, you can see we have more or less a homogeneous mixture solution. We have some uniform mixing going on. Whereas in B, you can see it's probably two separate phases, right? The blue looks like it's probably a solid, whereas the red is probably a liquid. Now for chemical reactions, right, when one or more substances react to form one or more new substances, and here we just, pot cooking some water here, we're going to make some soup. The reaction of methane with oxygen to form carbon dioxide and water, right? So that would be a chemical reaction. So we're going to actually take methane, we're going to combust it, and so we're going to mix it with O2, and the products that are going to be made are going to be CO2 and water. Right, so our reactants then would be CH4 and O2. Our products would be CO2 and H2O. Now, how do we picture that? How do we draw that out? Words, obviously, trying to write something out would be a little bit too long. Pictures might be too awkward. So a lot of times we use what's called a chemical equation. And again, this probably isn't new to most of you. If you're refreshing yourself on chemistry, if you just finished high school chem or Chem 110. Right, but we'll get into chemical equations in the next segment. I'm at 22 minutes, so this is a good spot where we can stop, a little transition spot. So we'll talk about chemical equations in segment 3. So we'll stop there, introducing you to chemical reactions.